questions on this first? All right, so any of those that you tried or attempted or whatever that you want to take a look at?
I started to try to do number 28.
In the book?
Yeah. I ended up just skipping it, but I tried to do it first.
What was it? What was it?
I forgot one.
X, and then quantity of 3x plus 2 to the 4th.
Like that? Okay. And what number was that? 28? All right. Yeah, let's take a look at that one. If you didn't have this one, it'd be a good one to work with us here then. You can count it as one of your extra ones to do for tomorrow's homework, right? So this was 20. This is similar to, there's one that we did in the other class with the LH packet. If I can find it here, this is very similar to, no, maybe it was a book one. I don't see it now right off the top of my head. Somebody got their book open. This is very similar to number 31. Yeah, this is very similar to 31. Now, what's easier about this one is it doesn't get into fractional powers as much as 31 does. 31 has to the 1/2 power, so you get into some fractions. So you got to be able to deal with that. But this one, so we talked yesterday about two different algebra situations that U substitution is good for. One of them was this, where we had, I think the example was something like this. And then when we do our U substitution, I don't remember exactly, but it ends up being something like this. Now, why is that second one better? Because we can do some algebra to it. In this case, we can split it apart. Because remember, everything we do, the whole point of all of these techniques, including the new one we're going to learn today, the whole point is to turn these integrals into this page right here, page 333. This is it. This is the only antiderivatives we know how to do. The ones right here. Now, and plus some variations off of this, like if it's e to the 2x, you kick out a 1/2. Or we got the sum rule, which says if you have 3 terms added or subtracted together in an integral, you can split that up into 3 separate integrals. You combine those things with these rules, and that's it. That's what we've got. You can't do a product. For example, on this problem here, we can't do the antiderivative of this and then do the antiderivative of this and stick those together. You can't do it. Just like you couldn't with derivative. You can't do that with a quotient. You can't do the antiderivative of the x and the antiderivative of the x plus 1. You can't do it. Okay? So the whole point of these techniques, and there's some other ones too. I mean, we're getting into some Calc 2 stuff here. And then the rest, or not the rest of Calc 2, but if you go on into more Calc 2 stuff, you get into more techniques of antiderivatives. We're doing U substitution. Today we're going to learn a new one called integration by parts. There's one called trig substitution. There's one called the method of partial fractions. There's some other ones too that you do to do these different antiderivatives. So our U substitution works on some problems, but it doesn't work on everyone. But what it does, what all of these techniques do, is they trade or they turn your integral that you're trying to do into a new integral that is easier to do. That's what they do. So like this one, we can split this apart into 1 minus 1 over u, and then we can split that into 2 separate things, and we know that that would be u, and this would be ln u, and then plus c, and so forth. Or the other one we talked about, and that's what this one is about, we said that if you have an integral like this, and then you've got some stuff to the 4th, we can't distribute that x through there. But what we will do is we'll turn it into an integral, and that's what's going to happen on this one, where we're going to end up with u to the 4th and then some stuff. And what can we do on this problem? We can then distribute that. and we can do some algebra, and then we can do our individual antiderivatives. So here's a couple of cases where U substitution will help us do that. Now, the easiest U substitution are the ones where we pick a U, the du is setting right there, we sub it out, it's a simple one, and away we go. But on some of them, we do our U substitution, and then we have to mess around with the new integral to get it into a form where we can make it work. All right? So, back to this. What is our choice for U? 3x plus 2. Now, this would have been easier if this would have been, let me show you, because one of my goals today for us is to recognize when we need to use U substitution. Because think about the gateway test. There's going to be some integrals on there where you don't have to use U substitution. All you have to do is maybe a little algebra and then just do basic antiderivatives. There's going to be some you have to do U substitution, and there's going to be some you have to do this new thing we're going to learn today, integration by parts. And you can't just pick one and do it. It's got to be the right one for that problem. And so one of my goals today is for us to look at a problem and understand why we would pick a certain technique. So in this one, this is a really nice U substitution here. Why? Notice how similar it is to this one. But this one's way better than this one. Why? Why is this one really nice?
6x for du.
The du, if you let u be the inside, the du is going to be 6x dx. And is there a 6x dx setting there? Well, there's not a 6, but who cares? We can divide that over, right? We can move that out. There's an x dx setting right there. So this one is a great U substitution one. And I want you to be starting to recognize that. I want you to be, when you look at one like this, right away you think, let u be the inside, the du will be x dx, which is setting right there. This is a good one for that. Now, the reason you guys ask about this one is you had some difficulty with it. Well, why? Because when you let u be the 3x plus 2, the du is what? Just 3 dx, and so that is not setting there. We've got this extra x there that's hanging out, right? That's the issue. Well, what, and we did one like this yesterday, think, what can we do with that? We can solve this for x. That is an option to substitute that out, and that's what we're going to do. Now, it does get kind of messy when we do it, but let's go ahead and finish it here. So, I'm going to, this part will come out nicely, and that's u to the 4th. The 3, I'm going to move over to this side, because I don't have that in there anywhere. But dx is equal to 1/3, and I'll leave myself some room here, du, right? So I sub that out easily, I sub that out easily, but that extra x is sitting there that's causing me some grief, but I realize that I can take this and I can solve. So I can subtract 2, and then I can divide by 3. Now the problem is, I see a lot of you do this. You do u minus 2 all over 3, and that's okay, but I think that makes these problems tougher. I think you should split that apart. Division is usually not useful or as friendly. I think fractions are better. So I would write this x as 1/3 u minus 2/3. I just think that's better. Now, I don't know if you could do it with the u minus 2 or 3, and that makes sense to you, go for it. That's fine, but I'd rather do this. So now in place of this x, I'm going to put 1/3 u minus 2/3. Okay? Now, I can kick out a 1/3. That's true. I could pull that 1/3 out of here. Now, we did one in the other class. I think it might have been 31, where it was like 1/3 and then 2/5. And then you didn't have something you could kick out. So, right? So, I'm not going to, but yes, you could. You could pull out a 1/3 there and make this 1/9, and that would make things a little nicer. But in the end, you're still going to have to distribute that 1/9 too, so it really doesn't matter. Okay? So I'm going to go ahead and distribute this, and when I do, so if you pulled it out, it would be there, but you're going to need it in the end anyway. What I'm going to do is I'm going to distribute, but when I distribute, I'm going to distribute this 1/3 through there with the u to the 4th. So I've got 1/3 u to the 4th times 1/3 u, that'd be 1/9, and my integral symbol's still there, because I haven't done antiderivative yet. That's 1/9 u to the 5th, minus 1/3 times 2/3, that's going to be 2/9 u to the 4th du. So keep the integral symbol on there, keep the du in there, because all I've done is rearranging some algebra. And this is a problem. If you haven't practiced some of these, then people miss these all the time on the gateway test because they're fractions, they mess up their fractions. They just miss up simple multiply. Okay? And you can only miss 2, and so you really hate to do it just on that. All right, now we're going to do our antiderivative. Now it's ready. Now it's page 333. Now we can just do power rule. So we raise that up to a 6, divide by 6. So that'd be 1/54th u to the 6th minus, I'm going to raise that up to a 5, divide by 5, that'd be 2/45ths u to the 5th. Those seem like weird numbers, but I don't think I've made any mistakes there. Seems reasonable. Okay, and then I'm going to put my x's back in. Don't forget that. You don't want to leave it like that on the gateway test. You got to put your 3x plus 2 back in. Okay, 3x plus 2 to the 5th plus c. So they do get messy. I mean, these algebraic ones especially can get messy. All right? And then the idea would be if we would do the derivative of this, it would end up getting us back to that, which I think it would. Okay? All right. So that's number 28. Now, you know what? This would be a good one. Get your calculators out. This would be a good one to talk about as far as simplifying or to check your answers on your calculator. Because I really think when you're working on your, now the website, next couple days we'll be talking about the website, practicing that, I think, over the weekend, getting ready and practicing. That's probably a good place to go at that point because we'll have done a lot of the LH ones. We'll still have some book ones you can go back and do. That would be a good place to go and review. So it will check your answers for you, so that's kind of nice. But if you're doing some in the book, how can you tell if you're doing them right? Well, you can type them on your calculator. So if we go to the calculator with this one, let's go ahead and type this one in. So we go to our integral symbol. We got x. I got to put a times sign there, otherwise it'll think those parentheses, it'll think it's a function. And then what was it? 3x plus 2 to the 4th. Is that what it was? Okay. So we go onto our calculator and we go ahead and we hit enter, and then we look at what they have, and that's nothing like what we have. Right? So then it's like, well, how do we know? And I showed you this with derivatives, but I don't know if you remember. So, yeah. So what you'd want to do is type in your answer and remind me what was our answer. 1/54. Oh, shoot. That's not what I wanted. Okay, we had 1/54, 3x plus 2 raised to the, what was it, 6th? What was it, minus, plus? Kind of slow because of the, oh, okay. And there we go. 2/45, 3x plus 2 to the 5th. And I hit enter, and it's not the same, right? Now, sometimes it'll simplify them and they'll be the same, and you can just tell, but they're not. And so you're wondering. So now there's two ways you can do it. You can, like if I type 2 = 2, it just says true. We tried this with a different problem in the other class. It didn't work. We grabbed this, hit enter, hit equals, then grab this, hit enter, and then hit enter. Yeah, and then it just kind of does that. so you have to do a solve. So if you do a solve, so for example, if I do 2 equals 2 and tell it to solve for x, it'll say true. So do a solve, go up and grab the one you know is the answer, the one you did with your integral, hit equals, then go up and grab the one you did, which is this one, hit enter, then go comma x, and then hit enter. Oh,
Thank goodness.
that's bad. Now wait a minute, maybe I typed it in wrong. Yours said true? All right, what did we do wrong here? Yeah, you don't worry about the plus c. 1/3 u minus 2/3, 1/3 u minus 2/3, 1/9 u to the 5th minus 2/9 u to the 4th. Raise that to a 6. Raise that to a 5. Problem is the book, the answer book doesn't always write it the same way either. What number was that? 1/54, 3x plus 2 to the 6th, minus 2/45, 3x plus 2 to the 5th. Okay. Yeah, I feel better about that. So, why is the calculator saying false? It's just, that is not, calculator doesn't want it. So it was this, is that right? X times 3x plus 2 to the 4th, right? Okay, so that should be good. Equals, and our answer was this one, right? Comma x. Okay, so much for using your calculator to. So what you want to do is take a picture of the answer book before the weekend. So you can look at that. Well, usually it works.
Let's try another one.
Well, we did one last block and it definitely worked. But yeah, we can do that. So let me do that other version of it that we did. Let me just grab that, hit equals, and then grab the one they simplified. I don't know why that. All given false. Huh. Well, there you go. Well, nothing's perfect, but that does work quite often. That's the first one I've ever seen. Well, I haven't done that many of them, but first one I've seen where that didn't work. So we did 31 in the other class. We did 31, and very much like this, and we typed it in, and it came out and said true. So a lot of times when you've done one and you want to see if you did it right, that is an option. If it keeps giving you false,
Or if you did it right, and then it messes you up.
it messes you up, and then well, life's not fair. Life's not fair. Call a friend, say, hey, here's what I got, and call, send a picture of it to someone. Preferably someone who gets it right a lot. Carly, send them to Carly, okay, and see if they did it right. All right.
Have our parents do it. And see.
Yeah, just have your parents do it. Check it for you. All right. So okay, another one. Well, let's talk about 31 because it's pretty much the same as 28. 59. Something kind of interesting happens with this one. We were looking at that, the snoon here. it says the integral of x, is it just x? What's 59? Somebody got, who's got the book? Justin, what's 59 say? All right. Again, this one is a nice u substitution because what I'm hoping is starting at least to jump out at you is that you could let u equal the x squared because the du is 2x dx. There's an x dx sitting right there, and that'll be 9. So you let u equal x squared. You let du equal the 2x dx, or not let it equal, but that's what it does equal because you do the derivative. And you get x dx. And so now you're going to get a new integral. The x dx is going to be out of there with a 1/2 and a du. And then this is tangent of u. What? Square root. Yeah, yeah. So the tangent, so we get this. Now, so that's a nice substitution, but there's a problem. We don't know the antiderivative of tangent. Right? Now, that list on page 333 is just the list that the book's authors decided were the ones you needed to memorize. That we could have added to that list. There are several basic functions are on there. For example, what's the antiderivative of tangent? It's not on there. What's the antiderivative of natural law? It's not on there. They're not complicated. They're just not straight backwards from the derivative rules like page 333. Page 333 is pretty much here were the derivative rules, so here are them backwards, and we use those. We could have added these to the list and said, hey, we're going to memorize it. But we did, and that's fine. So what this means is if you run into tangent, you're going to have another way of doing it. Well, it turns out we need to do a u substitution on this. This would be a double substitution. Sometimes this happens. I'm not going to make you do this on the quiz, on the antiderivative test, but this is how we would finish this problem. So we would write this as sine u over cosine u. And then we would do well, we can't do a u substitution because that is already being used. So a lot of times they use w for the next one. So we could let w equal what? Well, which one would you let w equal? Because it's the bottom. Remember how we often use the bottom. If you think about this, if you let w equal sine, then the dw, wasn't that Arthur, yeah, that's from Arthur, dw. dw, yeah, I heard that. dw would be cosine du, and we don't have a cosine du here. We have a 1 over cosine du, but we don't have a cosine du, so we wouldn't want to let u be sine, or w equal sine. So we want to let w equal cosine u, so the dw would be negative sine u du, which is setting there. And the negative we can move over to the other side, okay, divide it over. And so we would have this. So this integral then, let's do that in red. So this integral becomes 1/2 negative, the sine u and the du would come out and be the negative and the dw. And the 1 over cosine, or the cosine u on the bottom would be 1 over w, right? Well, what's the antiderivative of that? ln. So this is negative 1/2 ln w plus c. But w is cosine u, and u was x squared. So this is negative 1/2 ln cosine of x squared plus c. Remember yesterday we talked about whether you wouldn't need the bars? This would be one where you wouldn't need the bars. Oh, the squared is on the inside. You're right. Yes, it is. The square, it's in the inside here. It's cosine x squared. There it is. So we wouldn't need the bars. Okay? We wouldn't need the bars. So but the lesson of that is the antiderivative of tangent is negative ln cosine. So we could add that to the list and say memorize it. We're just not going to. but we could. So if you have tangent, the antiderivative of that is negative ln cosine. Okay? All right, so it ends up being that. So that was kind of an interesting one. There's another one that was in the LH packet. I'm not sure if anybody will ask about it, but I'm going to talk about it. Kelsey, you're the one that ran into that one yesterday, or you asked about it. It was this one here. 2 square root of x dx. What? That was number 24, I think, maybe, in the LH packet. Okay? Now, this one is a great example of another situation. Because what you need to, or what should happen on the gateway test is you look at a problem and you first should think, can I just do a basic antiderivative? Can I rearrange it, do some algebra, whatever, and do a basic antiderivative? If not, we think about u substitution. Now, we should recognize those pretty quickly, just like this one, right? Right away, we should look at that and say, hey, there's an x squared. I can do a du. That's going to give me the x dx. That's going to be a nice u substitution. Or it's going to look like the new ones we're going to do today, where we're going to do this thing called integration by parts. Okay? So that's the thought process. So on one like this, actually, I would hope you would recognize that you don't even need u substitution for this. However, some people did try u substitution. It turns out it works. Now, that's unusual. It's unusual when you can try u substitution and have it work when a basic antiderivative would have worked instead. Or it's also unusual to do u substitution and have a couple different ways to go and they both work. Not very many problems does that happen. Usually there's one way to get to it and that's it. Okay? So here's all the, I'm going to run out of colors here. Let me try this one in black first. So Kelsey, remind me what you did. You did square root of x. Okay, so one way of doing it is that. And then what did you do from there? I think you just recognized that that was... Yeah, that's interesting. But here's what happens a lot of times is people look at their du and they flip that down to the bottom and they say, wait a minute, that whole thing there...
Yeah, so that's what I ended up doing.
Yeah. So
I
what...
just had the integral of 1
Yeah, so one way of doing it is you look at it, you look at your du, you flip that down to the bottom, and you look at that, and you say, oh gosh, that whole thing is just du. Well, you got to have something in there, so you put a 1, right? Well, what's the antiderivative of 1? U plus c, which would equal square root of x plus c. Well, then you start thinking about it, and you think, well, yeah, that makes sense, because if it's x to the 1/2, the derivative of that would be 1/2 x to the negative 1/2, which is what that is. So then you say, well, so that worked fine. Now, here was a route somebody went in the other class, which I thought was kind of interesting, and actually makes sense the more I think about it. But what they did was this. They said u is equal to square root of x, which is this. Then they did their du, which is 1/2 x to the negative 1/2 dx, right? That all makes sense. But they didn't notice that this was this. What they did instead is they and you think about this, it kind of makes sense. We're so used to once we pick our u to be that we want to plug our u back into there, right? So what they did is they wrote their integral as 1 over 2u, right? Everybody see that? So u would equal x to 1/2, so that's that. But then they were stuck here because now they've subbed all that out, but now they don't have anything for their dx. So they looked at it and they said, well, wait a minute here. du is 1 over 2 square root of x dx. So they multiplied the 2 square root of x over to here. Now, normally we would want to avoid that because you don't want to mix up the u's and the x's typically. But then they said, but wait a minute, what's square root of x? That's just u. So then they rewrote it this way. And they said, well, dx is equal to 2u du. Well, that's true. So here they got that, and then, right? 2u, because u is square root of x. So square root of x is u. So dx is equal to 2u du. So they took the dx out and put in 2u du. Well, what happens there? 2u's cancel out, and you get 1 du, which is the same thing we had here, and they ended up with the same answer. Oh, that's interesting. That's a pretty cool way to do it. But then in the end, it turns out that probably the best way of all would have been to just write this as 1/2 x to the negative 1/2 and realize you just do a power rule. You don't even need u substitution. It's just this, you raise that up to a 1/2, you divide by 1/2, the 1/2s cancel, you get x to the 1/2 plus c, which was the answer anyway. So kind of a strange one because it works at kind of a variety of different u substitutions, or it wouldn't need a u substitution at all. Okay, so that's a good one to look at just to see what's going on. And again, notice that sometimes when you get into a problem, and I use an analogy of you're taking off and you want to go somewhere, and you've got 3 or 4 different routes you can go. So you take off on this one, and it's a dead end, and you got to come back, and then you got to take a different route. Well, this one turned out there was a couple different routes that all got you there. One was shorter than the others, but they did get you there. But sometimes you're going to go down a road that you're going to get stuck. You're going to come back, and you're going to have to try something else. All right. What else? Any others? Any others you tried, especially book ones or the packet, but you tried and kind of ran into a problem? We want to really, over the next couple of days, we want to try some of those in the book, especially maybe some of those at the end or some of them that look really hard. I mean, try those and just see see if you can get them. See if you can get them figured out. And those would be good ones to talk about if they cause you trouble.
41.
Which one? 41. Is this a book one? What do you got? You got your book? Did you write down the problem? Justin, what's 41? Thank you, Justin, for having your book open. Oh, yes. Thank you, Brian and Justin, for asking about this one. This is a good one, too. This brings in another little trick that we have not seen yet. Okay? And that's the purpose of all this practice, to find, just like when we were doing those packets, we run into all these little things and then that we can deal with. Now, a couple of things that you notice. So your first thought probably is what? Let u be the bottom, right? Not only that, bottom was one of the options we talked about, but if you let u equal x squared plus 1, the du is 2x dx. Oh, and then you think, geez, it isn't there. There's a plus 4, but adding really gets me into trouble. I can have x dx. I just can't add 4 to that and make it x plus 4 dx. That doesn't work. So, what else? Well, okay, let's back up here a minute. So what did I say for the gateway test? So the first thought is there anything I can do algebraically to rewrite, split it apart, something like that? You can't split a bottom. As long as you leave the bottom together, if you've got multiple terms on top, you can split it. So wouldn't it be legal to split this into this plus this? Now, we've never seen that before. We've never seen one like that before. But wouldn't that be legal? As long as we keep that denominator together, that is okay. Now, the nice thing that just did for me, now I can let u be the bottom on this one. And I'll have that x dx sitting there. And then what about this guy over here? Wouldn't be the same. Pull the 4 out in front. Arctangent. It's arctangent. 1 plus x squared. And now I was waiting to see if somebody would say that earlier. Anytime we have 1 plus x squared or x squared plus 1, same thing. On the bottom, arctangent at least is a thought, right? Now when there's an x up top, that wouldn't be a thought. But once we split it apart, sure enough. So here it's an arctangent. Here it's a regular u substitution. So we're going to do u equals x squared plus 1 on this one. The du would be 2x dx. We're going to move that 2 over here as a 1/2. We got our x dx. So now that x dx is going to come out and be a 1/2 du. The x squared plus 1 on the bottom, so this will be 1 over u. Right? So we got a natural log, so we got a 1/2 ln of u. The u is x squared plus 1. Now, do we need the bars? Won't x squared plus 1 always be positive? Gotta be, because x squared is going to be positive, or 0, and then you add a 1. So that's always going to be positive, so we would not need the bars. That'll be okay. You could leave them. That'll be fine. And this one, we pull the 4 out, and that's basically our tangent. Okay? So this is going to be plus arctangent of x plus c. What did I forget? I did forget the 4. That would really suck to miss one on the gateway test because you forgot 4. Okay? Yeah, just arctan of x, because it's whatever's squared there. Okay? So, good one. Thank you for asking about that one. So, those are, those are just some of the little things. We talked about splitting up, but we always did it when we just had like a u on the bottom, We didn't do it when we had something like that. But that is something we can do. Okay? All right. Let's go and talk about the new thing we have today, and then that'll leave you some time to work here. So, and then ask some other questions if you got them. So, what we're going to do next is talk about some integrals where u substitution is just not going to work. And again, u substitution is just one technique. U substitution is just, now you don't need to write this down. What we're going to do is develop a formula here. And we've done that before. We're going to develop a formula, and when we get done, that's the formula you'll need to know. So this part you don't really need to know. But all of these techniques are needed because there are certain antiderivatives that can only be done a certain way. All right, and that's why they were developed. Remember, the whole point of finding an antiderivative is to find a function so that when you do the derivative of it, it gets you that function. And so this whole art of working backwards causes us to have all these various things. We don't have a product rule. We don't have a quotient rule, right? We just have these ways of working certain ones backwards that, so that they get us the antiderivative that we're looking for. Well, this one is developed from the product rule. U substitution comes from the chain rule, right? It's used mostly when you have an inside kind of thing. Even when we do the bottom, that's really an inside. It's the inside of a natural log. The bottom, if you think about it, ln x, the derivative is 1 over x. If it's ln x squared, it's 1 over x squared, then times the derivative inside. So whenever we let u be the bottom, we're really doing an ln. We're really doing the inside of an ln. So u substitution is really from the chain rule. This one we're going to learn, called integration by parts, is really from the product rule. Okay? And once we get done with it, I'll tell you about which types of functions you look for to use this. Now, for your gateway test, it's going to be pretty easy. It's going to be, well, if it isn't a basic one, and if I can't use u substitution, then it's got to be integration by parts. I mean, that's the only thing that's left. Okay? All right. So here's your basic product rule right here. Now remember, u and v are both functions of x, right? This would be like sine x times e to the x or whatever, right? So they're both functions of x. So what I'm going to do is I'm going to do the antiderivative of both sides with respect to x. So I'm going to do the antiderivative of both sides with respect to x, which is legal, right? I can do that. Now what do you suppose you're going to get on the left side? Just u times v plus c. Now both sides are going to get a plus c, so we'll just ignore the plus c till the very end. Okay, we'll just ignore that because they'll both get a plus c, right? So the left side, you're just going to get u times v because you're doing the antiderivative of the derivative. They cancel each other out. You're just going to get u times v. All right, so let's write that. Or you don't have to write it, but let's see what we got. So left side just going to be u times v. This side, I'm going to have this integral with respect to x. All right, now I want to not write prime notation. I want to write the dx kind of notation. So what's another way of writing u prime? Du over dx. And v prime would be dv over dx, right? So let me write that. So same thing except u prime is du over dx. and v prime is dv over dx. Now, when I have an integral like this that has two separate terms in it, what can I do? Split it apart into two integrals, right? So I'm going to split this into two integrals. And so I've got that here on the next page. Okay, so I've split it now into two separate integrals. Now, what do you notice you can do there? What do you think? Cancel. And you can't. Cancel. And you can't. And now look what you got. You got a du and a v. Well, normally the du would be on the outside. And so we got that right there. Okay, now remember, u and v are, it seems strange that you're mixing like v with the u. Normally that should always agree. Well, remember, these are all in terms of x. V and u are both functions of x. It's like an e to the x, you know, whatever. So it's okay. All right, now I'm going to take this and I'm going to subtract it over to this side. Okay? So I get the integral of u dv equals this right here. Now, before I have you write this down, keep in mind what we're trying to do. U substitution, the whole point of U substitution was to trade our integral that we didn't know how to do for a new integral that we could do. Maybe with some algebra, but it would match page 333 and we could find the antiderivative. So that's the whole point of all these techniques. Trade our integral that we don't know how to do into a new integral that we can do. Well, that's what this is doing. This is going to be our integral that we don't know how to do. And it's equal to this, which gives us a new integral that hopefully we will be able to do. Okay? So this is what you would write in your notes then. I'm going to flip it around so it's on this side, okay, like that. This is called integration by parts. This formula you're just going to memorize. Basically, you're going to memorize the right side of this formula. But this is saying if we have our original integral, which we're going to call, it's made up of two parts, u and dv. So this is our original integral. That's going to be equivalent to this. And hopefully, that integral is one we can do. Now, our original integral is going to have a u in it. Our new integral has to have a du. How are you going to go from a u to a du? Do the derivative. Our original integral is going to have a dv in it. We want our new integral to have a v. How are you going to do that? That's the antiderivative, right? Going from dv to v would be doing the antiderivative. So within this technique, you're going to be doing derivative, you're going to be doing antiderivative, which is kind of what you did in the u substitution also. All right. So what our job is then, when we run into one of these problems, is to figure out what to let u be, which part of the integral should be the u, and which part of the integral should be the dv. Now it's not as, okay, so here's the first problem we're going to do. So we're going to do the integral of x e to the x dx. Right? Now, first let's just imagine this is the gateway test. You're confronted with this problem. What is your thought process? Can you just do it with a basic antiderivative? No, because it's got an x, got an es. Can you split those apart? No. Can you just do the antiderivative of that and the antiderivative of that? No, it doesn't work. So then you got u substitution. Now, what are your choices for what you could let u equal? You can let u equal x. Now, this is funny. This has never come up before in this class. So, don't write this down. But I always have some people think about it anyway. Let u equal x. Well, let's see what happens if you let u equal x. Du would be dx. And so when you substitute, you would get, that would be a u. This would be e to the u. And this would be, now why is that no good? Because you didn't change anything. The whole point of u substitution is change this integral into something new that we can deal with. You haven't changed it at all. It's the same thing. So u substitution, never, 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 never let u equal x. Never. Because it's not going to get you anywhere. Okay? Now in this new technique, that's not necessarily true. You'll see that in a minute. So u substitution is not going to work here. Right? We can let u equal e to the x, and then d would be e to the x dx. But there's no way you could get that x out of it. You say, well, you got an extra x. How about you solve for x? Well, if you let u equal e to the x, when you solve for x, what's x? ln u. So then when you sub out, you'd have ln u, and then e to the x dx would be the du. Do we know how to do the antiderivative of ln u? That's one of them we didn't know. We don't have a rule for it. What?
Is there a rule for it?
There is. Well, there's not. Well, yeah, there is an antiderivative of it, and so we could memorize it, right? But it turns out we need this new technique to get the antiderivative of it anyway, right? So you think, well, there's an extra x. We talked about that. We could solve for x. Unfortunately, you get down a road that's a dead end. You can't do it. Okay? So u substitution is not going to work. So we need this new thing. Now, I might make a comment here. I wouldn't have had to change that problem very much to make it a nice u substitution problem. Right? Because if this problem, so we're thinking about how we would be, thinking to ourselves on the gateway test. If I got this, then I'm going, oh yeah, u substitution. Let u be x squared. The du is 2x dx, which is sitting right there. That's great. And away we go. U substitution would get it for us. But not on this one. All right, so we need to do this. So here's how this works. This is our original integral. We need part of this to be u, and the rest of it to be the dv. So here's what our work looks like. We're going to write down our u underneath like we always do. And then off to the side here, I'm going to write dv, which will be the rest of it. Now, your challenge here is to figure out what to pick for the u and what to pick for the dv. Well, here's how you're going to decide. Well, actually, I'm going to give you a little shortcut on how to decide. But the way to decide is this. The thing you pick for the u, you're going to then do what? The derivative. So you want the thing you pick for the u to be something you can easily do the derivative of. But more importantly, whatever you pick for the u is going to leave you something for the dv, and you're going to have to do the antiderivative of that. And those sometimes are hard. Like, for example, we just said we don't know the antiderivative of log, right? So if I had a log in here, an ln in here, would we want it for the dv? No. So we would for sure want to pick it for the u if we had a log, because we can easily do its derivative, but we can't do its antiderivative. So the stuff you pick for the u is the stuff you can easily do the derivative, but you can't easily do the antiderivative. Now, conversely, the last thing you'd want to pick for the u would be the stuff that you can easily do the antiderivative on, right? Since there's some stuff you can't do the antiderivative of very easily, the stuff you can do an easy antiderivative ought to be the stuff you do here for the dv. Now, what's something you can do an easy antiderivative? E to the x is really easy. So that should be the last thing. So the first thing you should pick for the u. So if we're going to make a little list of what to pick for the u, the first thing we would want to choose would be the logs. The last thing we'd want to pick would be exponentials. Okay? Now, what's another function that's pretty easy to do an antiderivative? About as easy as it is to do the derivative. Powers, I would say, are pretty close. You're forgetting one of them. No, ln, we can't do the antiderivative.
No, the one over.
Oh, yeah, but yeah, that's kind of a specialized one. E to the x we already talked about. What about sine? Constant, yeah. What about sine and cosine? Right, derivative of sine is cosine. The antiderivative of sine is negative cosine, right? Pretty easy. So I would say that the next easiest as far as doing an antiderivative, so therefore one of the last ones we'd want to pick for you would be your trig. Right? Your trig ones. Now, let's go back to the beginning. What's another type of function that we don't know the antiderivative of? Now we talked about tangent, but that's in the trig. We're not going to probably deal with tangent. We won't worry about that. Think about the other type of functions we have. What about arc sine, arc cosine? Can we do the derivative of arc sine? What's the derivative of arc sine? 1 over the square root of 1 minus x squared. That's pretty easy to do. Do we know the antiderivative arc sine? Not at all. That's not in our list, right? Now, in our list we have, if you have the integral of 1 over square root of 1 minus x squared, that equals arc sine. But we don't have the integral of arc sine. We don't have a formula for that. So the inverse trig would be ones, I'm going to put an I for inverse trig. So L stands for log. The I is going to stand for inverse trig. Those should be our first choices for you, log and inverse trig, because we can do those derivatives, but we cannot do those antiderivatives. So we do not want those for the dv. So we want to pick those for the u for sure. And then the only thing left is the algebra, like you guys said, the powers. That kind of goes in the middle because they're about as easy either way. I mean, you can do the derivative of x squared, you can do the antiderivative of x squared, about equally well, right? So the A stands for algebra, the T stands for trig, like sine and cosine, and the E stands for exponential. We'll pronounce that liate. Liate. I came up, no, I didn't. It's actually in this book. It's not in all textbooks, but it is actually is in this book. But liate. And what that is a little thing we'll remember for what should we pick for our u. Because remember, whatever's left is going to be the dv. Because remember, this side of the formula is our original integral that we're starting with. So part of it needs to be the u, and the rest of it will be the dv. So liate tells us what we should pick for the u. So when we go to this problem, we have an algebra and we have an exponential. Which one should we pick for the u? The algebra, because a comes before the e in liate. It always goes with the dv, because you think of because when you think about your u substitution, your du and your dx, they always go together. So the dx will always go with the dv. So u is the x, and the rest of it, the e to the x and the dx, goes there. And you're right, when we do the antiderivative, the dx goes away, right? It always has, and it will in this case too. All right. Now, so you see in this case, in this integration by parts, it's okay to have u equals x. That's fine. In u substitution, no good. All right, so right under those, let's put their partners in. So if u is x, what's du? 1 dx. I would just write dx. We don't need the 1 in this case. And then if you got dv here, v is going to be the antiderivative. So what's the antiderivative? That'd be e to the x. And whoops. Oh, and we don't need the plus c because we're going to put that on at the end. Okay? So we'll just put e to the x. And the dx goes away because we did the antiderivative there. Okay? All right. So then it's just a matter of following the formula. So now we're saying our original integral, this guy here, is equal to u times v. So we look at our list. Here's u times v. So that's x e to the x. And it doesn't have an integral on it now. It was just, if you look at the formula, it's just u times v minus the integral of v, which is e to the x, and du, which is dx. Right? Now let me make another comment here before we finish. If this would have been like a 3x, our du would have been 3 dx. Now, I often see people divide that 3 over here like we do so often in u substitution. You don't want to do that in this. Because when you fill out your formula, you do u times v minus v du. You want to put here what du is. So if du is 3 dx, you want to put 3 dx in here. Right? So if you get a 3 or something here, you do not want to divide that over like we do in u substitution, okay? All right. Well, look what happened. Did we get what we wanted? We traded an integral we didn't know how to do for a new integral that is easy to do. And so we get x e to the x minus the antiderivative of that is just e to the x. Tack on your plus c, and you're done. And you can check it quickly. I'll do it in red here. The derivative of this, we need a product rule. So that'd be 1 e to the x plus x e to the x minus the derivative of e to the x is e to the x. The c would go away. The e to the x cancel, and we get x e to the x, and it works. Okay? So integration by parts. So the idea here is that There are some integrals where we can do the antiderivative with u substitution, but there are a lot of them where u substitution just doesn't work. So this is going to be a category where we can use integration by parts. Now, how are you going to recognize it? Well, a couple things. First of all, it's a mixture of functions. It's a mixture of function, I guess you'd say families. In the other class, I say it's like Romeo and Juliet. It's like the Hatfield and McCoy. I don't know. That is the best I can come up with. It's different function families. It's like a log with an algebra. It's like an exponential with a trig. It's right. Now, that doesn't mean every time you get that, you're going to have integration by parts. We just showed an example. This guy right here. Here's an algebra mixed with a exponential. But it's u substitution. That's because the inside thing makes it work nice. But usually an integration by parts is a mixture of function families. The second thing you usually get is a product. It's usually a product, right? Because it comes from the product rule. Now again, we've seen plenty of u substitution ones. As a matter of fact, almost every one we've done today has been a product, right? Well, that was a division. There was a product. There was a product, right? But those all had nice things where we could do u substitution on. Okay, but like this one's all algebra. It's not a mixture. See, that's not a mixture of different functions. This one, well, this one kind of is, but again, the u substitution works nice. Right? That's not a mixture of different functions. You're not going to do this integration by parts. We're going to stick with pretty much the basic ones for this integration by parts. So they're going to look kind of like this. All right? Let's do one more, and then I'll let you go to work. Integral of x ln x. Now let's make that x squared. Ln x dx. Again, you have a mixture of different function families. There's nothing that really stands out at you where you can let u be that thing. There's nothing on the inside where you could let u be that and things would work nice. So that's a real big hint that it's this thing. Now, to be honest, when you're doing your homework, there's going to be even a bigger hint, and that is if you're in the section of the book that's integration by parts, that's what it's going to be. If you're in the LH packet is all substitution. Okay? So you're going to kind of know, but hopefully you're thinking about that as you go. All right, so what do? Well, we need a u and we need a dv. Which one are we picking for the u? Natural log, because Liate says if you got a log in there, that's the first choice for the u. That comes before the algebra. So the rest of it, the x squared, the dx, that's going to be the dv. And you have to count for the whole thing, everything. Everything has to get used. So whatever you pick for u, the rest has to be the dv. All right, so what's du? 1 over x dx. And the v? 1/3 x cubed. And we don't need the plus c. If it bothers you that we're not putting a plus c, that's good, because at least you're thinking about how there should be a plus c, right? But we'll put that on at the end. All right, so here we go. We follow the formula. Formula says u times v. So I would write that 1/3 x cubed times ln x. Probably the easiest way to put those together. So u times v minus the integral of v, which is 1/3 x cubed, times du, which is 1 over x dx. Now, this time it came out a little messier. But is that new integral something we can deal with? You have to cancel out those x's. You cannot, and again, I always see people at this point want to do each of those individually. You can't do that. If we could do that, we would have done that clear back at the beginning. We can't do that. We're going to cancel this x and make, right? And so this integral is going to end up being, I could even pull that 1/3 out, and then like an x squared dx kind of thing. So my final answer is going to be 1/3 x cubed ln x minus, and now I'm going to do this antiderivative. So I'm going to raise that up to a 3, divide by 3, so that's going to be 1/9 x cubed, and then plus c. Now remember, the first part of integration by parts, the uv does not have an integral on it, so you don't have to do an antiderivative there. You just do u times v, but make sure to bring it along in your final answer. The second part is the integral of v du. Make sure you memorize that. uv minus the integral of v du. v du. simplify it if you have to, then you have to do the antiderivative, then tack on the plus c. Last thing, if this would have been a definite integral from like 1 to 5, we would have done all of this first, got down to the very end, left off the plus c, done our right bracket, 1 to 5, and then have done f of b minus f of a. Okay, so you do all that the same, find your antiderivative, leave off plus c, right bracket, and then plug them in. All right, so here's the homework. If you take out those homework sheets, so the ones I've circled here. So now, you know, I told you that some of these techniques are taught in algebra or in Calc 2, right? U substitution a lot of times is gotten to in Calc 1. Integration by parts is more like Calc 2. And notice it's in Chapter 8 in the book. Okay? It's not in Chapter 5, it's in Chapter 8, but I want to do it. So we just jump ahead to Chapter 8 and do that one section. So these circled ones here are the integration by parts. That's in the book. The other LH stuff, those are all U substitutions. So it's kind of a mishmash of various problems. And then you certainly can add on to that some of those ones in that big page in your book on page 340, right? At 23 through 73. Go back and do a handful maybe from there of practice. That's a good idea also. Okay? Tomorrow we'll look at some other situations that can arise with integration by parts. We'll do some review. I'll probably throw out some problems to you, have you do them, see how you do. Maybe throw out 10 problems, see if you can get 8 out of 10. Might do a little of that again on Friday and a lot of work time probably too. Nothing really new to discuss really from here on out. Yes?
Are any of them in that big group, integration by parts, or all those?
In the what?
That big group?
This one?
No, the
page 340.
the one with like 50 of them that we didn't like fix.
Those are all U substitution. That page 340 in the book is all U substitution. There's not as much integration by parts practice. Quite honestly, on the gateway test, there's probably only a couple of integration by parts. There's probably over half of them are probably U substitution on the gateway test. Probably a couple that are just basic antiderivatives with some rewriting maybe, and then a few of the integration by parts. So yeah, that big page where you just pick ones out, those are pretty much all U substitution. All right, go ahead and go to work.